first speaker today will be Kamesh Munagala, talk about competitive algorithms.
So this is joint work with Sangjin Im, who's in the audience here. He's a professor at UC Merced, and Janardhan Kulkarni, who is also somewhere here, and he's a postdoc at MSR Redmond. So the problem we are considering is scheduling. So let's look at the most basic scheduling problem. Right? So the most basic scheduling problem is scheduling on one machine. So suppose we have one machine that processes, it can process at most one job at any time instant, and it processes the jobs at rate 1. So whatever amount of work it has, it processes it at unit rate. We assume that as jobs come in, the scheduler can preempt an existing job and reschedule it at a later point in time. So it can arbitrarily interrupt jobs and reschedule them. So what do we know about a job J? So each job has some processing length Pj, right? And it arrives at some time Rj. Okay. So it's because the job arrives at time Rj, it's alive at some time T if T is bigger than, it's at least Rj. And it's alive if at most Pj units of processing have been assigned to it. So it arrived at time Rj, and if the scheduler assigned to it less than Pj amount of processing, that means, but the job has length Pj, so which means that there is still processing left to be done, so the job is still alive. So a scheduling policy is a policy that looks at the current set of alive jobs and decides, okay, which job should I process at this time instant? Okay. And the different policies differ on what they are trying to optimize. So we impose the following constraints on any reasonable policy. Firstly, that it's online, in the sense that the scheduler doesn't know about the existence of a job before the job comes. So when the job arrives at time Rj, the scheduler becomes aware that the job is alive, that the job exists. Right? And the arrival process of the jobs is adversarial. So there's a standard online algorithm setting that the jobs are coming in online, and the job J arrives at time Rj. The scheduler doesn't know about the job before time Rj. The other constraint we impose is that the scheduler is non-clairvoyant, which means that it's not aware of how long this job is. So the job has some length Pj, but the scheduler is not aware of what this Pj is. After time Rj, it becomes aware that this job exists. It's allocating some processing to it, but it doesn't know when this job is going to complete. And both of these are sort of reasonable assumptions in sort of realistic scheduling settings. So there are many objectives that the scheduler could try to optimize. The objectives we are interested in is what are called related to the completion of the jobs. So for job J, let Cj denote the time at which the job completes, and that would be the first time at which it receives Pj units of processing. Okay. And a related metric is what is called Fj, which is the delay of the job, which is the time when the job completes minus the time when it arrives. This is how long the job took to execute. Okay. And the objectives that we'll consider in this talk are the sum over the jobs of either the completion times or the flow times. So that would be called the total completion time or the total flow time. Just by dividing by the number of jobs, you can also think of them as the average completion time of the job or the average flow time of a job. Okay? So we want to design a scheduling policy that sort of is online and non-clear. Actually, that's my next slide, I think. And the framework that we are considering is like, how do we analyze the performance of an algorithm or a scheduling policy? We'll do that in the framework of comparative analysis. And this is standard in online algorithms. Sort of in comparative analysis, we say that for every input instance I, we look at the total sort of cost of our algorithm, which is to say the sum of the completion times or the sum of the flow times, and we want to bound it by some constant times the best possible that any algorithm could have done, right? And the best possible for defining opt, we assume that opt knows the entire sequence of jobs in advance. It knows the entire processing, exact processing lengths of the jobs, and it does the best possible, right, to minimize either the total completion time or the total flow time, right? So this is like an offline optimum, and we want to design a scheduling policy that is online and non-clairvoyant, right, and which can be within some constant factor of the best possible you could have done had you known the entire input. This is standard in online algorithms. So for this, for the sort of scheduling problem that I defined, there are many algorithms that are constant competitive. So there's shortest remaining processing time, round robin, shortest elapsed time, and so on. The two that I've put in bold are algorithms that are non-clairvoyant, which means that they don't know the processing length of the job till it completes. Okay. So I've just briefly surveyed what single machine scheduling is. In the rest of my talk, we will not focus on single machine. Our goal is to go beyond single machine scheduling. And now I'll define a very general scheduling problem that builds on the single machine scheduling. So if you think of what single machine scheduling is, right, you can write it as an LP. Right? You say that any feasible policy for this single machine scheduling problem defines a set of linear constraints. Okay? And if you look at, for this LP, the variables are yjt, which is the amount of processing that you assign to job j at time t. Right? So what are the constraints on this, on any feasible policy? Firstly, there is only one machine. It's processing jobs at unit rate, which means that the total rate that it assigns to the jobs at time t is at most 1. Right? It is splitting this rate 1 among the jobs that it has at time t. Right? And the other constraint is that each job has to be completely processed. Right? Which means that if you look at the rate that job j gets across all time instants, right, it has to be at least the processing amount of the job, or pj. Right? Is this clear? If you have questions, just interrupt me. Right? It's like sort of, it's just saying that there's one constraint for every time step which says that at most 1 unit of processing rate can be assigned. It has one constraint for each job saying that the total processing that you assign to it is at least the length of the job. That's all. Right? So you can think of the constraint at every time t as some kind of packing constraint. Right? It says that the total rates that you assign is at most 1. Okay? So it's like what is called a downward closed constraint, that if any set of rates is feasible, then rates which are smaller than it are also feasible. So in this talk, the way we are going to generalize it is to say that instead of having this constraint that sum of the rates is less than or equal to 1, we'll have a general set of constraints. Let's say that the rates that you assign to the different jobs belong to some packing polytope. Right? And we don't care what this polytope is. I'll give you several examples of problems that can be modeled this way. Okay. So the overall problem formulation is that jobs arrive over time in an online fashion. Okay. Job j has some processing length pj that is not known to the scheduler. Job j finishes processing if the total rate assigned to it is at least pj. And there is a packing polytope p on the feasible rates that can be assigned to the jobs at any time step. And the goal is to design a scheduling policy that minimizes the sum of the completion times or the flow times. In terms of LPs, the rates that you allocated every time instant belong to this polytope. For every job, if you look at the time, if you sum the rates from the time the job arrives to when it completes, it is at least pj. And you want to minimize the sum of the completion times. This is not really an LP because cj depends on your policy, right? But just ignore that fact, right? So this is minimizing the sum of the completion times. Okay? And a scheduling policy is a solution to this program where before time rj, the scheduler doesn't know about the existence of the job, and pj is not known till the job completes. Okay? So it has to satisfy these two other constraints as well. So far, so good? Yeah.
We're allowed to interrupt jobs?
Yes. It's all preemptive. None of what I'm saying works if jobs cannot be interrupted.
Is the total number of jobs known in advance?
No.
So yt is some vector that
Yeah, so we'll assume that like as jobs arrive, you get to know how p expands. Like the current polytope you can compute. Okay. I'll give you several examples and it'll become clear what this p is. Right now p is very abstract. Okay. So let me present some. So basically pretty much any reasonable scheduling problem you can think of can be written in this framework, assuming you can preempt jobs and reassign them, and assuming you can do some kind of randomized assignments. Okay. So the first example is what is called unrelated machine scheduling. This has been sort of extensively studied in within the theory community and beyond. I'm just presenting one reference here, but there are many other works on this topic. So you have jobs, you have machines, right? For any job, the rate at which different machines process it is different. So if you assign this job J to machine I, it processes it at rate Sij, right? But you can, at any point in time, you can preempt the job and assign it to a different machine. That is allowed. Okay. So jobs can be preempted and can migrate across machines. Different machines process jobs at different rates. The rates of processing are known to the scheduler. When the job arrives, you know at what rates the different machines will process it. The only thing that you don't know is how long this job is. The other constraint is that the job cannot be processed on multiple machines simultaneously. You can preempt it and migrate it, but you can't process it on 2 machines at the same time. And so so roughly speaking, at any time step, the assignment of jobs to the machines defines like a fractional matching. Okay. So assuming that you can do some kind of randomized assignment. So if you write it in terms of packing constraints, right? So let Xij denote the amount to which job I is assigned to machine J, right? So each machine can process at most one job. So that is this constraint, right? Each job can be assigned to at most one machine. That is this constraint. And the rate at which the job is processed is simply the sum over the machines of the speed of the machine times the amount that you have assigned the job to that machine. Okay. So this is like a set of packing constraints, and this has to hold for every time step. So the overall problem would be that you have these packing constraints for every time step, and that would define your rate that the job J gets at this time step. You also have this constraint that the total amount of processing that you assign is at least Pj, and subject to that you want to minimize the sum of the completion time. So okay, this is an example of how unrelated machine scheduling can be written as a special case of this problem. A more sort of recent problem is what is called multidimensional scheduling, and it has like sort of because of all these data centers and multi-core architectures and so on, this has become sort of a problem that has been widely studied in computing systems. So in this setting, it sort of flips thing around. You can think of it as there are jobs and there are resources. Each resource is available to a certain amount. That's called, say, resource D is available to an amount RD. In a data center setting, you can think of resources as CPU, RAM, disk, and so on, or you can think of it as many different types of machines. Like there are many ways of, you can take any setting and sort of model what the resources are. At every point in time, the job can be allocated a certain amount of each of these resources, right? And the speed of the job or the rate of its execution depends on how much of each resource you allocate to this job. And the other constraint is that the amount of resources you can allocate, amount of any resource you can allocate is at most its capacity. Okay. And again, so sort of the practical motivation, as I mentioned, is scheduling in data centers, right? Most of you must have seen this problem in some form or the other. So anyway, just to write it as packing constraints. So let Xdj be the amount of resource D that you allocate to job J. So the total amount of resource D that you allocate is at most its capacity. And the rate that a job gets is some function of the different resources you allocate to it. Okay? And this function is, let's assume that it's like it's a concave function, so that this whole thing is a convex space. Okay? Just to give some examples, so the only thing that I didn't specify is what is this Uj. Okay, before that, then again, the overall problem becomes at every time t, you have this polytope, and that defines the rate of the job at time t. And as before, you want to minimize completion time. So some common utility functions are, these terms are borrowed from economics. So in Leontief utilities, the rate at which the job is processed depends on sort of the bottleneck resource it gets. So you look at all the resources, the amount of resources the job gets in different dimensions. You take the min over the dimensions, and that defines the rate of your job. Okay. So it's sort of, in economics terms, these are called complements. So the job needs all the resources to run. Okay. And complements are one extreme case, right, where the job needs everything to run. But you can think of various models which have substitutes. So the rate doesn't depend on the bottleneck, but it depends more smoothly on the different dimensions. And a common utility function again in economics are what are called CES utility functions. If rho is 1, this is just linear. So jobs rate is linear in what it gets in different dimensions. If rho is 0, it's something called Cobb-Douglas utilities and so on. Right? In fact, there are architecture folks at Duke who have done data model fitting and shown that Cobb-Douglas is a reasonable model for this multidimensional resource allocation. But sometimes in data centers, people also use Leontief. Okay. I could present a whole talk on like different problems that can be modeled in this way, but that will get boring. All I want to say is that there are a lot of problems that have been looked at in the theory community, including by many people in this room, and they can all be modeled in this framework. So there's multi-commodity flow routing, there's broadcast scheduling, speed up curve models, and so on. I won't define these things. Basically, all you need is that you need preemption, and you need like some convex space of randomized assignments or fractional assignments every time step. Right? Under those assumptions, pretty much anything can be written as a convex program. So, right?
So what does this in the Cobb-Douglas when rho tends to 0? What does it correspond to Leontief? No.
When rho is minus infinity, it's Leontief. When rho is 0, it's something called Cobb-Douglas, which is the product of x raised to a. That's roughly what it looks like.
So, Kamesh, the different models you presented in this slide, basically they all reduce to convex optimization.
They can be written as like you're doing some allocation to the jobs at every time step, subject to some constraints, right? And as long as you allow randomized allocations, you can think of it as a convex space. What are our results? We show that for this general problem, there is a algorithm that is online, non-clairvoyant, and it minimizes the total completion time to a constant factor, compared to the best algorithm that knows the entire input in advance. And the same thing holds for flow time, but it doesn't hold for all problems that can be written in this framework, but for a natural subclass of these problems. I'll define what this subclass is a bit later. But on the other hand, we show that for the general PSP problem, there cannot be any constant comparative algorithm for flow time. Recall that flow time is the sort of delay of the job, which is the time it finishes minus the time it arrives, right? And so the total flow time would be summing the delays of the job. And it's typically a harder metric to optimize than just minimizing the times at which the jobs complete. We show that there cannot be any constant comparative algorithm for flow time, but for natural subclasses, we can get constant competitive. And the interesting thing we show is that this can all be done by one algorithm. We don't need to design a separate algorithm for each problem.
So even with the resource augmentation, there is no...
Yeah, so this result holds only with resource augment. Yeah, so yeah, here I'm implicitly assuming, for those familiar with resource augmentation, I'm implicitly assuming that the online algorithm gets a constant factor more resources compared to the offline algorithm. So it's constant speed, right? And the lower bound also holds with constant speed. Right? If you want to get a constant competitive algorithm, you need super constant speed. That's what it is. I'm not going to mention the speed anywhere else in the talk because it's sort of it's a technicality and you need it for designing online algorithms in this framework anyway. So I'm just going to ignore it.
Also for completion time.
For completion time, you don't need speed because it's completion time. So okay. So before I present the algorithm, right? I mean, what is an intuition? I mean, what do we want to do, right? Because we are trying to minimize the sum of the completion times or sum of flow times, any algorithm has to sort of favor small, short jobs. I mean, if it completes many jobs quickly, then it's better because it's minimizing the sum of the completion times, right? So it has to favor the short jobs. But the policy, because it doesn't know the lengths of the jobs, doesn't know what the short jobs are, right? So in some sense, it needs to be fair to all the jobs because it doesn't know which the short jobs are, right? In one dimension, the fix is essentially round robin. You just assign equal processing to all the jobs. So this is the case where you have one machine, right? I mean, you just assign processing to all the jobs. You don't know which guy is going to finish fast, but you're just hedging your bets. And you can show that works. Right? But once you go into PSP, it's not even clear what round robin means. So let me just give one example, right? So think of multidimensional scheduling. You have D resources, okay? And there is this job that requires all the resources to 1. Let's assume that the resources have supply of 1, they have capacity of 1, right? This job needs all the resources to 1 unit in order to run. Okay? There is this job that only needs this first resource, it needs it to 1 unit. This job only needs this resource, the second resource, this job only needs the third resource, and so on. Okay? So at any point in time, you could either have scheduled this job, it takes up everything, or you could have scheduled all these jobs. Okay? And let's assume all the jobs are available at time 0. And you want to do some kind of round robin, because you don't know which guys, maybe this guy was a short job, maybe these guys were the short jobs, you don't know what. Right? Okay. So let's say there's square root D of these jobs, and there's 1 of each of these jobs. So there are totally D of these jobs here, 1 of each type, and there's square root D of these jobs. And let's say that all the jobs have length 1. The scheduler doesn't know this. Okay. One thing you could do is to perform round robin in each dimension. You take each dimension and assign processing equally to all the jobs that want that dimension. So if you take this dimension, there are square root D of these jobs that want this dimension, and there is 1 of this job that wants this dimension. There's square root D plus 1 jobs. If you split this resource equally among all these jobs, you would give like sort of 1 over square root D amount of resource roughly to all these jobs. So you do that. So the rate that you give each of these jobs is 1 over square root D, and the rate you give this job is 1 over square root D. Right? Because they're square root D of these jobs, each of them you're giving 1 over square root D of the resource in each dimension, so they'll get rate of 1 over square root D. It's 1 over square root D plus 1, but I'm ignoring the plus 1. Right? And same for these jobs. Which means that all the jobs are running at roughly the same speed. They all have length 1, so they all complete at roughly times square root D. Okay? They're totally D plus square root D jobs. Right? So the total completion time is D square root D. So this is a widely implemented algorithm, and it's essentially in systems communities it's called the dominant resource fairness algorithm. I mean, it's a slight generalization of this is called dominant resource fairness. Right? So it's not an algorithm I made up. I mean, this is something that people really use. Right? And so is everyone following this? Does this will have a completion time of D times square root D? Okay. What is the optimal thing to do? The optimal thing to do was, like, suppose you knew that these jobs have length 1, right? You will schedule all of them at the first time step. You can do that because this job wants the first resource, this job wants the second resource, and so on. So you'll get rid of D jobs at time 1, and then at time 2 you schedule one of these big jobs. At time 3 you schedule one of the other of these big jobs, and so on, right? So Op schedules all these jobs first. So these D jobs have completion time of 1. That's the total completion time of D. Okay, and these square root D jobs have a completion time of roughly square root D. That's another total completion time of D, so opt is order of D. Right? Which means that, and the completion time of this DRF was D square root D. That's a gap of square root D. Right? So this shows that this algorithm, this max min fairness or DRF, cannot be constant competitive. Right? You could say that, I mean, you should have done this, but I could have changed the lengths of the jobs, and then this wouldn't have been the right thing to do. Right? I mean, if these jobs were super long, then they should have been scheduled later. Okay. So the right algorithm is something called proportional fairness. And what it does is it maximizes the product of the job rates every time step. So at every time t, it calculates rates such that it maximizes the sum of the logs of the rates subject to the rates being feasible. Okay. And this idea of maximizing the product of the rates has been known in economics since at least Nash from 1950 and so on. It's been sort of studied in networks and so on. Right? So it's not something we came up with. What does this mean? So this essentially corresponds to something called market clearing. So what are you doing, right? I mean, if you take this resource allocation setting, you are maximizing. So you want to allocate resources to the jobs such that the total amount of resource you allocate is at most its capacity. The rate that a job gets is some concave function of the resources you allocate to it, and you are maximizing the product of these rates. if you think of rates as utilities, right? I mean, the utility of a job, you're maximizing the product of the utilities. It's well known, at least since the time of Nash, that this corresponds to a notion of market clearing, where you think of each job having $1 of money, okay? And what you do is set prices for the resources. So if resources D is priced at PD, so this price will correspond to the sort of dual variable of this constraint. Then what the job J, so each job individually tries to do the following. It maximizes its utility subject to the total amount of money it spends being equal to its budget. So it has $1 of budget. It spends the money given the current prices such that it maximizes its utility. If every job does that separately, then this market clears, which means that every resource is allocated exactly to, every non-zero price resource is allocated exactly to capacity. Okay. So a solution to this program corresponds to finding a setting of these prices such that the market clears. Every job selfishly optimizes its rate, and that is feasible. So it's been known in economics because of this motivation. So in our example, what does proportional fairness do? You have to set prices for these resources. It's symmetric, so you set equal prices for these resources. Regardless of what prices you set, this job wants all the resources, this job wants only one of the resource, so it can buy way more of this resource than this job, right? Because this job has budget of 1, this job also has budget of 1, right? I mean, this job will buy D times as much resource as this job can, because this job wants all the D resources. So this job will get rate roughly 1 over D, and this job will get rate roughly 1. Right? So it is doing the right thing in the sense that it is going to schedule all these jobs first before it schedules these guys. So, and it is not, it's not a coincidence that this happens. What we show is that proportional fairness is indeed constant competitive for the total completion time. And it's a non-clairvoyant algorithm because you didn't need to know the length of the job. If you look at what proportional fairness is solving, right, it just needs to know this polytope, and you're just maximizing the rates. Right? So it is a non-clairvoyant algorithm. The same thing holds for flow time, but for a natural subclass of these problems. And let's dig into what this natural subclass is. Okay, the subclasses for flow time are, our algorithm is constant competitive for flow time or delay whenever the proportional fairness algorithm is monotone. And what I mean by monotone is that when a job arrives, when a new job enters the system, the rates of all the existing jobs, so proportional fairness is doing some rate assignment every step. New job comes in, right? Then that only hurts the existing jobs in the sense that their rates must go down, right? And when a job leaves the system, then all the existing jobs are happier in the sense that their rate only goes up. You can think that this is a very natural property, that a new job is only introducing more contention, so it should reduce the rates of existing jobs. But it turns out that this is not true for all. There are PSP instances that don't satisfy this property. In fact, if you have Leontief utilities where the job's rate depends on the min that it gets in the different dimensions, it's easy to show that the proportional fairness algorithm won't do something monotone. In fact, like suppose you think of this job arriving first, right? It gets some rate, right? Suppose these jobs arrive next, right? Then the rates of these jobs actually go up. And these jobs arrive next, the rates of both these jobs will go up and the rates of this guy will go down. You can think about it, but that's how it behaves, right? So if jobs that need a few dimensions arrive, they help jobs that need complementary dimensions, right? This monotonicity is not a general property that every instance has. It only holds for certain subclasses. So what are these subclasses? So if you have multidimensional scheduling, but with like sort of gross substitutes utilities, which means suppose the utilities look like this, they are not Leontief, the job doesn't need all the resources to run, but it gets a reasonable rate even if it gets something in different dimensions. Right? So it's like one extreme is linear, but you can think of stuff beyond linear. But it shouldn't become that the job's rate depends on the min of everything. Okay. So for these kind of utility functions, when a new job arrives, the prices of all the resources, the dual variables in the proportional fairness, they only go up, which means that existing jobs can only buy less stuff. And the other special case is when this polytope that defines the feasible rates is something called a polymatroid. I won't define what a polymatroid is. And there are many sort of scheduling problems where the set of feasible rates is indeed a polymatroid. There's related machine scheduling, single sync routing, and so on. So these are like reasonably well-studied problems that fall in polymatroid. And this result is not ours. This is from Jain and Vazirani. They sort of look at these markets that this proportional fairness convex program defines, and they were looking at it from an economics perspective, and they're asking, okay, when does a new agent introduce more? When does introducing more competition hurt the existing agents? And so they sort of, this proof I think was known from before, but the proof that polymatroids actually satisfy this monotonicity is due to Jain and Vazirani. Okay. So in the remaining sort of 15 minutes I have, let me try to present some ideas of the proof, right? I mean, how will the proof go? So let me first present the proof for flow time, because it's sort of, I can at least try to present a reasonably complete proof. Okay. So the first thing is that like proportional fairness does not have a closed form. Right? In simpler scheduling setting, if you come up with a scheduling algorithm, there is at least some closed form for what that thing is doing. Proportional fairness, you're solving a convex program. We don't know what rates it found. I mean, it's hard to like sort of write a formula for what it does. Right? So we have to use some kind of optimality properties, that it's either doing some market clearing or it's something else. Right? We have to use some like equations about what it is doing. Right? So one thing is, like, if you just look at the gradient condition for what proportional fairness does, it's relatively easy to show that suppose at any point in time, y denote the rates that proportional fairness assigns, if you were to maximize the product of the rates. And let y prime be any other feasible rates at that time step. Okay? Then because y was computed by maximizing the product of the rates, you can show that if you look at the sort of the gain of y prime over y, like for job j, suppose y prime was giving you more than j. Look at the fraction by which y prime was larger than y. Right? If you take the average over all the jobs, that's at most 1. So in a sense, on average, a job couldn't have gained by going to some other, if you had used some other rate vector. Maybe some jobs gain, but there'll be others that lose. Right? And on average, it's at most 1. Okay. And in particular, this holds for like sort of the optimal rate assignment at that time step. The other property is like sort of that we can derive from the previous property, and this is something new, is what we call as prefix fairness. Right? So suppose the jobs are arriving as 1, 2, 3, 4 till n. Like the first job arrives, the second job arrives, and so on. And whenever, like suppose there are k jobs in the system, the first k jobs have arrived. Suppose you ran proportional fairness, then job j would have gotten some rate. That's denoted by yjk. Right? So this is the rate that job j gets, assuming only the first k of these jobs have arrived. Okay. Then what you can show is, so consider this ratio, right? This is saying, okay, this is the rate that job j gets when it arrives. When job j arrives, it's like the first j jobs, what rate does it get? This is the rate that job j gets if all the jobs arrive at the very end of the process. Right? I mean, you'd expect that this guy will be smaller than this guy, right? I mean, if more jobs arrive, it will hurt the rate of this job. Let's assume that, right? So this is how much the job j's rate gets hurt, right? The claim is that the average hurt is, so on average, the final rate is at least 1 over e times the initial rate. Right? Look at what happens when job j arrived, right? Finally, its rate is not that much smaller than what it had right now. But this is again only true on average across all the jobs. It's not true for every job. Right? I mean, so round robin is a special case of proportional fairness, and for that you can work it out that, yeah, this thing is, in fact, you can show n over 2 actually for round robin. But what we can show is that this is true for all proportional fairness instances. So, and the proof idea is simply that you can take this optimality condition of proportional fairness, right, and write it out for every subset of jobs. Right? You can say that, suppose there were k plus 1 jobs in the system. Right? Look at the rates that every job is getting. Right? Now, the rate that they would have gotten had there been k jobs in the system is some other rate vector. Right? And we know from proportional fairness optimality that the sum of this must be at most k plus 1. Right? This came because of this optimality condition here. I mean, you can take this, you can set this to whatever you want, right? In fact, you can set it to what happens to job j had there been k jobs in the system, right? So you can get inequalities of this form, right? And now you can combine all of these to show something like this. Right? Look at, as each job arrives, you add it, look at the new rate vector that proportional fairness would give, and say, okay, look, the old guy is related to the new guy in this fashion, and you keep doing this. Is that roughly clear? So basically, what I'm trying to say is that this optimality condition is fairly powerful. Because of this, you can set this to be any rate vector you want, and you can use it to prove different kinds of stuff. Right? And that's where we get sort of the, otherwise we have no handle on proportional fairness. This is the handle we get. Okay. So now for the, so intuitively what have we shown, right? I mean, on average across jobs, each job gets a reasonable rate compared to opt. That's just the optimality condition. And each job's rate is not significantly affected by arrivals departures. I mean, it's sort of, if more jobs arrive, its rate is hurt, but not by more than a factor of 1/e. But the thing is, these things only hold on average, and converting this intuition into a proof is tricky. And in fact, to make the proof work, we need that the proportional fairness is a monotone algorithm. Okay, so analysis of flow time, right? So we'll use a potential function analysis. I won't go into the details, but I'll just give you a high-level idea of what a potential function proof is. Okay, so first thing to note is flow time is measuring the delay of all the jobs, which is that when the job finishes minus when the job arrives. If you think about it for 2 minutes, you can also write it as, just by interchange of summation, sum over all the time of how many jobs are alive at that time, how many jobs have not finished processing at that time. Right? So total flow time is a sum over all the time of the number of jobs that are alive at that time. Right? So this is an easier quantity to work with. The second step is to say that, okay, look, if we are using a potential function, we need to sort of argue, we need to have some handle on how far behind proportional fairness is compared to the optimal solution. Opt is doing something, we don't know what it's doing. Proportional fairness is doing something. We have to sort of argue how far behind proportional fairness is. Right? So the variable that captures how far behind proportional fairness is, let's call it the lag, which is for every job j, look at how much processing time, how much processing is left for j in proportional fairness, how much processing is left for j in opt. Right? And this difference captures how far behind proportional fairness is on this job compared to opt. Is that clear? So this is, PJT is how much of job j is left to be processed by proportional fairness. This is how much of job j is left to be processed by opt. So this difference is, okay, how much behind are you? That's the lag. Clear? So the potential function we define is sort of measuring how much behind proportional fairness is. So it's essentially summing the lags. But we also give some importance to how much rate proportional fairness is giving to this job. If proportional fairness is right now giving a lot of rate to this job, we sort of don't count that lag as being very important. Right? Because proportional fairness is trying to do something reasonable for this job. So this phi will be high for a job only if lag is large and proportional fairness right now is like sort of not doing well on that job. Right? That means on this job, proportional fairness is really behind and our potential will be really high. Okay. And we don't take this to be the rate of the job, but only the rate of the job assuming, so you just take the subset of jobs that arrived before this job and look at the rate proportional fairness would have assigned had this subset of jobs been in the system. The reason we need to do this is because we don't want this potential function to jump abruptly if jobs arrive and depart. I mean, it's sort of, I don't want to get into that, but there is a reason why we need to define it this way as instead of just rate of the job at time t. So it's the rate of the job only considering jobs that arrived j and before. You look at that subset of jobs, recompute proportional fairness on that, what rate would it have assigned to job j, take that to be here. It's somewhat magical, right? Just bear with me on that magic. The rest of the proof is fairly clear. Okay, so what do we need to show, right? We need to show that if proportional fairness has a large number of jobs, right, then it is reducing the potential at much faster than how much opt can increase it. So if you look at this potential, right, if opt does some processing, it increases the lag because it goes ahead of proportional fairness. If proportional fairness does processing, it decreases the lag, right? So opt increases the potential function, proportional fairness decreases the potential function, right? And what we want to claim is that if proportional fairness is much behind opt, it has a huge number of jobs compared to opt, then this potential, then it is decreasing this potential much faster than how much opt can increase it. Okay? In other words, we want to show that if you look at the number of jobs that proportional fairness has in time t plus the rate of change of this potential, then its constant factor times the number of jobs opt has at time t. Right? If you integrate this over time, this will be the total flow time for proportional fairness. This will be some constant because it's a potential function, and this is, so it will be within constant factor of the total flow time of opt. Okay? So what we want to show is that if this guy is large, then this derivative is negative, sufficiently negative so that it sort of cancels out. Okay, so this is the potential. So if you look at what happens due to opt processing, so opt is increasing this guy, and it's increasing this guy because it's processing the jobs j, but it's processing job j at rate say y star jt, right? So the rate of increase of the potential will be this guy, sum of the job j of the rate of processing job j divided by this guy. And because of the optimality condition of proportional fairness, we can bound this in terms of the number of jobs in proportional fairness, because we know that proportional fairness is optimal on this kind of ratios, right? So it's at most the number of jobs in proportional fairness. So opt can't increase the potential too much. Now if proportional fairness processes, it decreases this guy. It decreases by the rate of processing of this job divided by this guy. And we have shown that this quantity is already at least the number of jobs in proportional fairness divided by a factor of e. So proportional fairness is actually decreasing this potential at a sufficiently large rate. Right? And now if you like sort of give proportional fairness some additional power of e, like you make it process e times faster, then this guy cancels out with this guy. So opt, whatever opt increases it by, proportional fairness will decrease it by corresponding amount and cancel with it. That's the idea. So basically we just used this optimality property of proportional fairness, derived a set of conditions, and used that in the analysis of this potential function. We didn't use any closed forms, nothing. Right? And that's the main idea of the proof, that like you sort of try to argue about how much, try to bound what opt can do in terms of some potential by saying that, look, proportional fairness is optimal. So let's write some condition on what this optimal means and show that this can't be too large and this can't be too small. And that's the basic idea. There are details in the proof. I still didn't explain why you need this less than equal to, but right, I mean, it'll take me too long to get into all that. I'll skip over this. We use a completely different proof for completion time, which is based on dual fitting. There I can't give you, like, it's hard for me to give you much idea on what goes on, so I'll skip over it. So let me come to some open questions. The big open question that we think is, if you take Leontief utilities, we don't get anything for flow time right now, almost nothing, right? Because for Leontief utilities, the one example that I showed, stuff is not monotone, so we can't use the analysis that I did for flow time. That only works for monotone instances, right? A new job comes in, it can increase the rate of some other job. And there we have almost no clue how to analyze stuff. So just recall that in Leontief, the rate depends on the minimum that you allocate in all the d dimensions. And the reason we want to study this is it is the most practical setting, and a lot of real scheduling problems that people care about in practice actually have Leontief utilities. Like if you look at scheduling packets in any like sort of switch or internet router, you can model that as a Leontief scheduling problem. Right? And same for data centers. In fact, Leontief is so general that, like, what is Leontief, right? It's just you're writing a set of inequalities, one for each dimension, packing inequalities. You can take any packing polytope and write it as a set of inequalities. One, like the number of dimensions might be large, but hey. So any PSP instance can be reduced to a Leontief instance, maybe with a large number of dimensions. So it's in some sense, this is the most general thing. Right? And we know that we can't get constant comparative. We have a lower bound saying that we can't get a constant comparative algorithm for flow time. But even something which depends by a small amount on the dimensions is okay. Right? I mean, in reality, maybe the number of dimensions is not that large. Maybe you just have CPU, disk, and memory. You have 3 dimensions. What the heck? It's not that bad. Right? And the main technical hurdle is we don't really understand these non-monotone algorithms. Right? And we don't understand what proportional fairness does. We don't have a good handle on what it does if stuff is not monotone. Right? And it maybe needs like, yeah.
So is the algorithm broken, or is the...
We don't know if the algorithm is broken. So it might work. We want a very weak guarantee, so we don't know if we don't have a counterexample. And we have a different algorithm that gives it's exponential. I mean, the comparative ratio is exponential in D. It's, I think, 2 raised to square root. I don't know, I've forgotten what it was. What is it? 2 raised?
Log with D to the D.
Log D to the D. Okay. On the other hand, if all jobs have length 1, then we know we can get a D comparative algorithm. It's, I think, D or D square, I forget what. But it crucially needs to know that the jobs have unit length, and it's also a very different algorithm from proportional fairness. This was in an iCalc paper just recently. So that's the status. I mean, if jobs have unit length, we can do it, but otherwise it's exponential. And these algorithms are sort of not as natural as proportional fairness. And we feel that some variant of proportional fairness should do it, but we don't understand these kind of non-closed form algorithms very well. There are some other directions, and these are more open-ended. Suppose you have, instead of 1, so typically in single machine settings and so on, people have looked at stuff with precedence constraints. One job depends on another job and so on. You can look at the same thing here, but you can encode like really hard problems if you do this, like job shop scheduling and so on. But if utility functions are more reasonable, they are not like absolute worst case utility functions, right? Or the PSP instance is reasonable, can we say something? And the one thing that I haven't addressed is, suppose you knew the length of the jobs, then do the problems become any easier? We don't know. I mean, we know proportional fairness does well, it's not clairvoyant, but we don't know any clairvoyant algorithm that does any better. Right? So yeah, we don't know. And there are other objectives we haven't considered, and those are all interesting, like make span, fairness, and so on. That's it.
Time for questions? So for the float time result, for the class for which you got, I guess, constant speed, do you know you can't get scalable algorithms?
We don't know. Maybe, I'm pretty sure you can.
For that class, you might.
Yeah, proportional fairness is not going to give it to you because it reduces to round robin, and round robin is not. But there should be some modification of it that gives you, but we haven't so far succeeded.
Any other questions? Let's thank Kamesh again.